You know that super fast fiber internet you might have at home? Ever really stop and think about what's going on there? It's kind of magic, right? You've got this tiny, super delicate cable, and it's bringing you gigabit speeds just by shooting little pulses of light through it. I mean, it's literally light, traveling down a tiny strand of glass, delivering your movies, your messages, everything. How amazing is that? Okay, let's get into it.
So the big question is, how does that even work? I mean, how in the world do you trap light inside a cable and then use that to connect the entire planet? It sounds like something straight out of sci-fi, for sure. But the crazy part is, the reality is built on some, well, beautifully simple physics. And that's what we're going to do today. We're going to break it all down.
All right, here's the game plan. We'll start with the whole quest for speed, then get into fiber's three main superpowers. After that, we'll see how the light actually stays inside the cable. Then we'll look at the two main types of fiber, figure out why good old copper is still around, and finally, see how this all plugs in to connect our world.
So to really get why fiber is such a big deal, you kind of have to look at what it replaced. For decades, our whole digital world ran on plain old copper wires. Yeah, I'm talking about the Ethernet cables we all know and, well, we all know them. The thing is, copper, it has its limits.
Okay, so the biggest difference, the real game changer, is what they're using to send the data. Copper sends information using electrical signals, and the problem with electricity is that it's really susceptible to something called electromagnetic interference. You'll hear it called EMI. Just think of it like static or noise that gets in and messes with your data. But fiber uses pulses of light, and light is just a fundamentally cleaner, way more efficient way to send all those ones and zeros.
So, what makes light so much better, right? Well, it really boils down to three key advantages. And I like to call them fiber's superpowers. These three things are exactly why fiber has totally changed the game for modern networking. Okay, superpower number one, and this one's the most obvious, speed. I mean, come on, we're talking about the speed of light here. Now, to be fair, technically the light inside a fiber cable is about 31% slower than it is in a vacuum, because it's moving through glass. But that is still ridiculously fast. We're talking measured speeds in the hundreds of terabits per second. Yeah, terabits with a T. And get this, theoretically, the bandwidth potential is pretty much limitless.
All right, superpower number two, distance. Fiber can go far, like really far. Your typical copper Ethernet cable, it starts getting weak after just about 100 meters, but fiber has this incredibly low attenuation, which is really just a fancy way of saying the signal doesn't fade away. To put that in perspective, some fiber cables can carry a signal for up to 100 kilometers. That's like 60 miles, without needing any kind of boost at all. It's wild. And that brings us to superpower number three, immunity. Fiber is totally 100% immune to that electromagnetic interference we talked about, the EMI. See, since it's sending light and not electricity, it doesn't create any of those disruptive electromagnetic fields. What does that mean for you? Well, it means you can pack dozens of fiber cables right next to each other, and their signals won't interfere at all. No crosstalk. You just get a perfectly pure, clean signal every single time.
Okay, so we've established it's crazy fast, it goes for miles, and the signal is crystal clear. But wait a minute, how do you keep the light from just leaking out of the cable? I mean, it's a tiny glass tube, right? Well, the answer is just a beautiful, brilliant little piece of physics.
The magic trick here has a name, total internal reflection. I know, it sounds super complicated, but the idea is actually really simple. Imagine you're underwater in a pool and you shine a flashlight up at the surface. If you get the angle just right, the light won't escape into the air. Instead, it'll bounce off the underside of the water's surface like it hit a perfect mirror. That's it. That's the principle.
So here's how that works inside the cable. The cable has a center part called the core. That's where the light zips along. And wrapped around that core is another layer of glass called the cladding. When a pulse of light traveling through the core hits the edge of that cladding at a really shallow angle, they call it the critical angle, bam, it reflects perfectly, right back into the core. It never escapes. It just keeps bouncing and bouncing, perfectly trapped, for miles and miles and miles.
All right, so now that we know the basic physics, you should know that not all fiber is created equal. There are really two main flavors you're going to run into out there, multi-mode and single mode.
And honestly, the biggest difference between them is just the size of that inner core. Multi-mode fiber, it's got a bigger core. This lets the light kind of bounce around on multiple paths, or modes, as it travels. It's great for shorter runs, like inside an office building or a data center, and it's a bit cheaper.
Now, single-mode fiber has a ridiculously tiny core. It's so small that the light basically has no choice but to travel in one single path, straight down the middle, like a laser bullet. This means the signal doesn't get jumbled up, so it can go for those massive distances we talked about. This is the stuff they use to connect cities or even run under the ocean. Oh, and a little pro tip, you can often tell them apart by their jacket color. Aqua or orange usually means multimode, and yellow is almost always single mode.
Okay, so if single-mode fiber is this amazing, undisputed champion of speed and distance, you might be asking a pretty logical question. Why on earth do we still use copper Ethernet cables at all? And the answer, well, it really just comes down to boring old practicality.
For starters, 3 big reasons. 1. Copper is just plain cheaper. A lot cheaper to make and to install. 2. It's way easier to handle. You don't need a bunch of expensive, specialized tools to put a connector on the end of a copper cable. Plus, it can carry electrical power right alongside the data. You've probably heard of power over Ethernet. Super useful for things like security cameras or VoIP phones. And third, let's be honest, the RJ45 Ethernet port is just everywhere. It's the universal standard on pretty much every device, and it just works.
But when it comes to the real backbone of our modern world, fiber is absolutely king. There's no contest. So let's zoom out for a second and just appreciate the massive scale of how this one technology connects, well, everything.
Think about it. It starts small, right? With that one little cable coming into your house, giving you those insane internet speeds. But then that cable connects to a bigger network, one that links up all the office buildings and data centers all across your city. And those city networks, they all plug into the global backbone, these absolutely massive undersea fiber optic cables that literally stitch the continents together.
And these undersea cables, they are true marvels of engineering. I mean, they're wrapped in heavy armor to survive the crushing pressure and everything else on the ocean floor. And to keep the signal going, they have these powered repeaters about every 60 miles. What these little boxes do is they catch the faint light signal, turn it into an electrical signal, boost the heck out of it, and then turn it back into a brand new powerful pulse of light to continue the journey. They do this over and over across thousands of miles of ocean just to connect all of us.
But you know, after all that incredible complexity, the global networks, the undersea repeaters, the whole shebang, it all comes back to this one simple, amazing idea. I love how the tech creator Network Chuck says it. He just holds it up and says, it's literally light traveling down this little bitty cable. And when you think about it that way, it's just incredible. The sum total of human knowledge, all our movies, our conversations, all being carried by simple pulses of light down a tiny, fragile strand of glass.
So here's what I want to leave you with. In just a few short decades, we've gone from old, crackly phone lines to sending data at pretty much the speed of light through glass. We've essentially mastered how to communicate using light itself, and that leaves us with a really fascinating question, doesn't it? As we keep pushing the limits of what this technology can do, what's next? What's the next leap? Could something like quantum communication come along and change the game all over again? It's pretty wild to think about.